And we can continue with Antti's final part and maybe some more questions. And we can organize some extra lectures by some other participants if there's something you cannot cover. So we have plenty of time in the program to have more discussions also. So go ahead.
So actually, in the stress business, I didn't tell you at all about conformal blocks or anything like that. I trust that Bajun will talk about that on Friday, I suppose. Yep. So there is a story. Then we have the stress and the T and the T bar and the what identities for both. And the upshot when you continue from the story, when you go, you get the picture of correlation functions written in terms of sort of quadratic or sesquilinear combinations of holomorphic and anti-holomorphic functions of the basically the moduli of the underlying geometry. And so there's a nice story there. You didn't touch it, but I will do now a similar story which enters here. It's again, things are sort of expressed in terms of holomorphic and anti-holomorphic, but not in the complex structure of the surface, but in this gauge direction. Okay. So let's do the. What was that? All right. So let's now just look at the AZ bar. So let's look at smooth forms on the surface which just depend on one forms which are just in the DZ bar direction. So here, if you wish, 0, 1 forms. So these are differential forms where the coefficients take values in the complexified Lie algebra, so SL2, 2 by 2 complex matrices with a 0 trace. And then let's just define a Katz-Moody block. So let's look at smooth forms and let's take a holomorphic map from the space of smooth such forms to this tensor product of representations. Like our correlation functions took values in such a space, tensor product of representations, so that's the motivation here. Which have the transformation property what we had before. Here I was sort of writing such formulae, so where I was varying only the Z bar component. So let's look at such guys. So a function of a smooth one form, when you transform the one form with this gauge transformation, the end result is just this anomaly term, and then the sort of natural thing where you rotate with the h, this tensor product of matrices. Okay. Oh, this is math, so you can just look at anything. So let's look at this. And now ask, clearly there is something here that we are moving sort of, there's of course an infinite dimensional space of h's which I can put here, and for each such h we have this formula. So the fact is that actually the set of such guys which satisfy this rule is actually a finite dimensional space, on the finite dimensional space of such things. And it depends on the points, which I call mistakenly by x, so it depends on these zi's. It depends on the set of representations we have here, and it depends on the surface. The space of these gammas is finite dimensional, and the reason for it is that when you look at this infinite dimensional space of smooth forms like that, then this action here, that's an action of the group of the transmitted transformations, namely a group of smooth maps from the surface to the complexified D group. So that's SL2C in our case. And so this group acts on this space. So the gauge transformations act on the spatial connections by this formula here. And this gamma is sort of a function almost invariant under this action. I mean, there are these sort of simple things out here. So the orbit space turns out to be a finite dimensional space. We saw some of this, well, didn't see. I mean, I told you that on the sphere, every gauge field like that can be written as a gauge transformation of nothing. So the orbit of 0 on the sphere covers almost every gauge field. I said that it's a dense open set, so it doesn't cover everything, but it's a dense open set. And you understand also the ones which it doesn't. So this space is finite. This orbit space is actually finite dimensional and lying a little bit. It's something which can be compactified. So it's a finite dimensional, let's say, think about it as a finite dimensional compact complex manifold. And if we have this rule is some sort of holomorphicity, so we have some sort of holomorphic function. It's not a function because it's a transformation law. It's a holomorphic section of a certain vector bundle on the surface. And the space of holomorphic functions you are used to on complex surfaces should be sort of a small space. And in this case, it's a finite dimensional space. And there's a finite dimensional set of solutions. Those of you who know about Chern-Simon's quantum field theory, then this is the same space as the quantum Hilbert space of the three-dimensional Chern-Simon's quantum field theory. That's a topological field theory, which has the property that the Hilbert space, the quantum Hilbert space, is finite dimensional, actually, not infinite dimensional like usually in quantum mechanics, even though a single particle.
What is the relationship between the quotient space,
Yep.
the orbit space, and the solutions to that equation? Like, there's something that.
Well, if this was completely invariant, so if this factor wasn't there and the R's weren't there, then this gamma would be constant on the orbit, right? So you would just need to pick each orbit and give a number. Right? And then you ask how many orbits are there, and then it's the orbit space. So here it's slightly more complicated because there's this transformation law on the orbit. So you have this vector indices and it's rotating this, and now the space is finite dimension. Okay, our word identity earlier, where was it? Earlier here. This word identity here, where is it? Here. The AH is missing. Here I had one where I rotated both AZ and AZ bar. So I had twice as many things coming, and I multiplied from left and right. So I have now two of such guys. So it's a natural thing to guess that the correlation function in the Wess-Zumino-Witten model in the presence of the gauge field, well, it's supposed to satisfy the word identity. Gamma satisfies half of it, gamma bar the other half. So let's take a sesquilinear combination of them. That certainly would satisfy the word identity. And now the question is, what should I should have some coefficients here. And so that would be a conjecture, the correlation functions of the Wess-Zumino-Witten model in the presence of gauge field. I could put A to 0, and then I would just have the original Wess-Zumino-Witten model. I would have solved. This is a proposal of a solution of the Wess-Zumino. We don't know how to define the functional integral. But we could now, doing all this song and dance, we end up with a conjecture of what could be consistent conformal Kac-Moody field theory, namely the correlation functions given by this formula, if we come up with a formula for the coefficients here. And it's natural, again, to think about this in the following way. And this interpretation comes from the Chern-Simons theory, because you have sort of Hilbert space. I said that these gammas are vectors in the Hilbert space. And what would be a natural sesquilinear thing in a Hilbert space? That's a scalar product, of course. So you're looking for a scalar product. And there is a natural scalar product here, again, written in the infinite dimensional set, completely formal again. I have functions of the A and the A bar, and just take the white noise scalar product, okay? So, take exponential over the formal functional integral. But think about this, this is really Gaussian, so this is like a white noise in the space of connections. And then you have these functions defined on the space of connections. And you take their scalar product, they are vector values, so you take scalar product in these representation spaces, and then integrate over the connections to come to that.
So you have the invariant scalar product for the group. It's in the representations?
Yeah, this is the usual invariant scalar product for the group.
So I don't understand how Wess-Zumino-Witten, so the left-hand side of that equation is correlation function for Wess-Zumino-Witten, right?
Yeah.
And the right-hand side, though, is something else, right? It's like, it's about Chern-Simons or...
Both of these satisfy the same word identity, okay? This, we don't know how to define, but we did all these transformations and we believe that it satisfies the word identity. Its dependence of A is given by the formula what I wrote. Gamma I defined to you to satisfy the word identity. So gamma and gamma bar together satisfy the combined word identity. So such a combination would be a solution, and that would be a neat solution if we came up with what would be a natural H to put there. And the conjecture is that, is it like that? If you're interested, if you do the Polyakov-Witten formula calculation, then you pick up the paper by Witten from 1995, I think, and there he shows that you can actually, if you take just one here, just a partition function, just using Polyakov-Witten formula and this, you can actually prove this by doing formal path integrals. So this guy actually did that. Okay. So there's some evidence that this should be an interesting way to study it.
So the product on the bottom, can you decompose into the orbits and then...
Which product?
The last one?
The
path integral?
Where is the product?
Yeah, this one.
The scalar product.
Well, this path integral, can you decompose it in terms of orbits and...
Yeah, that's how I do here. Yeah. Okay, so how do you then compute? Well, I said that you do that, but who knows how to calculate this, right? What does it mean? Well, I mean, you use the word identity again, because you parameterize the space of connections by, I told you that the orbit space is not on the sphere, there's only one orbit, so on the sphere you could just parameterize all the A's by H, that I did to you already when I computed the word identity. If you are on a more general surface, then there are some moduli. So there is a finite dimensional set of connections which parameterize all the orbits, and then there is an orbit of each such a guy. Okay, so you parameterize your gauge field by this fixed moduli connections, and then the infinite dimensional orbit. And now you plug that into the scalar product here, the gamma, and you use the void identity what we had here, this property, this definition. Okay. So once I plug that in to the scalar product, then there's a little bit of calculation, because you get what do you get? You get all these factors, and then from the other side you get the other one. Okay. You plug it into this formula here, get that one, and then some R's. Okay. Sorry about the R's. They sort of carry out simply there. So you get some S factors, and when dust settles, you use again the Polyakov formula. Everything once you combine all these terms, comes rather simple. You get Wess-Zumino-Witten model again. So the dependent. Let's just consider the partition function. So gamma, there is nothing here, no representation matrices. Okay. Then all what comes is exponential of S of now H times H star. There are two of them because HZ bar and HAZ both have similar things here. And then you take the Wess-Zumino-Witten action on not on a matrix which is H times its Hermitian conjugate. H is a complexified SL2C valued matrix, and I take H star and compute it with this fixed moduli gauge field. And then you have to do a little calculation of the change of variables from this formula to the formula for a measure on H and M. If you are interested in that, that's done in the paper by Govetsky and myself a long time ago. And again pops out this thing, and this is for Baptist especially. Here you get the dual Coxeter number again, and so altogether, once dust settles, the end result is the following. For instance, if I'm on the sphere, let's not worry about higher geometry. On the sphere, the inner product of these two Kac-Moody blocks is given, there are no moduli, so it's given by an path integral over matrices which are over the form H star with a Wess-Zumino-Witten action, where K is modified by something coming from the group. And so to define this scalar product, we should now understand the Wess-Zumino-Witten model not on the unitary matrices, but on positive matrices. This is a really long story to justify why one should study such a thing, but the upshot of these discussions is that there's some sort of, one expects there to be, for many reasons, a connection between the Wess-Zumino-Witten model, which we didn't really have. We have only the formal path integral, and the Wess-Zumino-Witten model, which also has a formal path integral, but now the matrices are positive. And now I claim that this particular path integral we can understand probabilistically. Okay.
What is DHH star?
I'm sorry?
What is, like, in the formula in the middle, DA Z bar is, yeah, that one. So what is DHH star?
Yeah, some sort of Lebesgue measure in the space of positive matrices. I will define it in a second.
Is there a canonical measure on this A model?
I'm sorry?
You have a canonical measure on A.
Canonical measure, this is up to you now to pick up a measure there. Yeah,
Yeah, but is there
In the SU2 case, this can be done rather explicitly. Yeah, there is a nice parameterization that can be done explicitly. But in general, it's a rather messy thing, as you can imagine. Okay, that's the end of the story of a long story starting from the group-valued sigma model and ends to a positive matrix-valued sigma model. Okay? So now we can forget everything and start from scratch. This I skip. Okay. And then this was one motivation to study Wess-Zumino-Witten model, not on unitary matrices but on positive matrices. There are other reasons for it, which I want to now talk more about. I suppose Colin will talk about it next week.
No, in June.
In June? And next week nobody talks about it. What is Remy going to talk about?
Remy's not talking.
Remy's not talking.
He's organising.
Okay, too bad.
We'll see what we can
Well, maybe somebody is here.
We can have informal lectures.
Okay, anyway, so let's now decide that we are interested in, and let's take now fix SU2, okay? And let's look at the Wess-Zumino-Witten action, which we wrote down, but let's now, instead of unitary matrix, put there a positive matrix. In positive matrix, you can write as H star, where H is a complex matrix, right? And if you write it as H star, it's obvious that you have too many degrees of freedom. Namely, if I multiply H from the right by a unitary matrix, then it cancels out here, right? Because H star, then you get UU star, and that's 1, okay? So clearly, what is involved here is only SL2C divided by SU2, namely modular unitary matrices, and I can choose the unitary matrix so that I can decompose any complex 2 by 2 matrix as a unitary matrix times an upper triangular matrix. This should be familiar from linear algebra. Okay, so we can take the H here upper triangular. It has to have determinant 1, and it's complex. Okay, determinant 1. And there are 3 parameters. So on the diagonal I have number and its inverse, and then in the off diagonal I have some complex number, and let me write it like that. So the number and the inverse I call e to the phi over 2 and e to the minus phi over 2. That's just convention. And I put also the phi here. Okay. So here are coordinates in the space of positive matrices. I can use such coordinates, 3 coordinates, 1 real and 1 complex, phi and gamma. So the space of complex, the space of positive 2 by 2 matrices is just, topologically, it's just real numbers times complex numbers. Just nothing, no topology anymore here. Like SU2 is a sphere, but this is just 3-dimensional space. Okay. And now if you plug into the sigma model action which we had before, such parameterization, you end up with such an action function. Rather nice, right? I mean, there is a sort of a Dirichlet energy of the phi, some sort of Dirichlet energy type thing of the gamma, but that's multiplied by exponential of the phi, so it's not exactly. It's a very non-linear thing. This is what comes out, and if I compare it to what we had in the sigma model, you see that this is exactly what you would get if you would take the following space, namely the 3-dimensional hyperbolic space. Let me write the gamma, the complex gamma in terms of real and imaginary parts. So gamma 1 and gamma 2 are real numbers. So three-dimensional hyperbolic space, what we'll consider here is, there is a mistake, there are too many squares here. So it's R3 with a metric. First variable is just the Euclidean metric, so this shouldn't be here, second square. And in the two other variables, there is a d gamma 1 squared, Euclidean, well, also parentheses wrong, okay, d gamma 1 squared and d gamma 2 squared. Because gamma 1 and gamma 2 times e to the 2 phi, okay? I think you get the idea what it is. So that's a hyperbolic space, so it's R3 but with a particular metric. You take that and put it into the first lecture formula for the sigma ball, you end up with this action. The topological term in the Wess-Zumino, actually, since this space is topologically trivial, you would expect that it's actually is a local action, and it's an instructive calculation to compute it. Okay, it's a homework for those who are interested. It's done in our paper also. Anyway, it comes, it's interesting how it comes. It comes very similar, no term like that, but there's another, these gamma pieces come sort of in, with a, one comes with a minus sign, and once you add them together, you get such an action. So that's very simple looking, right? And this is action which we believe to give rise to a conformal field theory now, because it comes from the Wess-Zumino-Witten model.
Is one of them the derivative with respect to z?
I'm sorry?
Last formula?
Yeah, in the last one it seems the derivative is respect to, but
This is pretty
z
bad,
would cancel and the z bar would.
One should be z, yeah. This should be
But
dz.
also in the gamma term.
This is dz. dz
Okay,
comes from,
yes, I guess
yeah.
from these, yeah.
Yeah, that cancels.
I think
Oh.
there are some signs which are.
Which cancels? Minus.
Minus the z bar.
It should be z bar. You mean.
It should be?
Well,
Okay,
you see it better. from
if
there.
all of these other
There's a
ones are correct.
minus dz bar. Yeah, it should be dz bar. Yeah, this cancels with that.
Yeah. Okay.
It should be. Doesn't matter.
Sorry, the topological term, is that not supposed to be over 3 manifold? Or?
Well, we are. I'm writing it that we are just on the sphere here, but we can be on any manifold. Yeah.
The topological was a boundary of a.
You're talking about the target space. Yeah, that's just the three-dimensional, just R3. In ratio 2 case, it's 3 sphere, and now it's just R3. Okay. That's what we got here.
No, I'm not talking about the target, I'm talking about the source.
The source.
The source is 2D, right? But
Yeah.
to write the topological term, just you have to go to
Yeah, of course, it was defined, it was defined by, like before, but now I tell you that if you now put this parameterization, what we have, well, I have the proof here, in general, okay? Okay, I do it for a general group here, so we are supposed to write this when g, little g, sorry, not capital G, little g is h star. Do a little calculation. The trace of the cube of that, when you put h star there, is a derivative of something. That's a calculation, okay? I give it here, the calculation, it's not complicated, okay? But if it's a derivative of something, then you can integrate by parts, and then you get in the end here, okay? That's the calculation. And it works for any semi-simple Lie group. Okay, so maybe I can do Colin's talk. All right, so now we are supposed to make sense of this path integral. You were asking before here, but what does this mean here? Yeah. So here's the answer now. Well, first of all, let's still be non-rigorous. So it should be an invariant measure. So I talk about Haar measure. Now we are in the space of positive matrices, but the group SL2C acts on this hyperbolic space just by multiplying the H by G, okay, from the right, like that. And then the invariant measure, you can now compute what is the invariant measure of that action in these our coordinates, and that's what it is. Again, if you like calculations, that would be an interesting calculation. Yeah.
And just to be sure, so the fact that you can write this logical term, the local functional of, is because you can write G as a H stuff.
Yeah.
Yeah. So it's completely general, it does not depend on the fact that you consider it U2.
Yeah, it is algebra, yeah. In the general semi-simple group, this is just the natural star, okay. But in metric group, it's just the Hermitian conjugated.
It's important you have the complexified group. So that
Yeah, exactly, yeah. Okay. So that's what the measure would be. So we want to do, let me just call it, and the capital DH would be just the product of all this, again the formal product of all this, but again completely formal. So we would like to define this path integral now, probabilistically. And there are some calculations you have to do. We do a couple of formal calculations, and that gives us an idea how to give a rigorous definition to it. Okay. So let's be on the sphere. Let's suppose work just on the action, and let's think everything to be smooth in the beginning. So let's look at the, let's take phi to be smooth and look at the gamma term, okay? So this is a quadratic form, right? And by integration by parts, I can write it as in the product of gamma with some differential operator acting on gamma. And the differential operator is just when you integrate that by parts. So you have dz bar. Here I have the correct thing. dz bar e to the minus 2 phi, because that's there, and dz bar adjoint. Okay? That's sometimes called this kind of operator. If phi were 0, this would be just a Laplacian, ordinary Laplacian, but when phi is non-zero, it's sometimes called the Witten Laplacian. But anyway, this is a positive operator, right? Because it's clearly this is a positive operator, and here is the guy and its adjoint. So it's positive on the L2. It has for smooth phi, it has a discrete spectrum like Laplacian, and it has actually. It's a non-negative, so it has a zero mode, namely the constant function is annihilated by this operator.
So you assume surface without boundary.
Yeah. Here we are.
Sphere. Yes.
At the moment, I should be on the sphere here. Yeah. It's a sphere. Here it looks sigma is C hat. Okay. And it's easy to find out. Well, so. When phi is fixed, the gamma is sort of, we should try to define it as a Gaussian measure, right? Because it's quadratic in gamma. So we are interested in the covariance, which is the inverse of the operator which is upstairs here. So I can invert this operator, since it's positive and discrete, etc. And it has actually a Schwartz kernel, so and you can write it concretely in the. You should, of course, do it in the orthogonal complement of the zero mode. It's basically the Schwartz kernel of dz bar. That's just the Cauchy transform. And then you have to subtract something in order to be in this orthogonal complement. Basically just the Cauchy transform of your volume. And that's an explicit formula for the covariance. So look at just what comes out. The covariance now has some nice looking terms here. An exponential of 2 times phi. It starts to smell like Gaussian multiplicative chaos, right? Because phi is supposed to be, in the end, not smooth, but Gaussian free field. So that looks sort of promising. So for phi smooth, anyway, we could just define this path integral over gamma as follows. It should be just like, and now I refer to Morris. Yesterday he defined Liouville. How did he define the Liouville? He just said that you write your field gamma in terms of the zero mode and the rest, having the covariance what we wrote before. So I take a Gaussian field with that covariance, then I add the zero mode. I take expected value over the gamma and integrate over the zero mode. That was his definition of Liouville. But here we do it for this gamma integral. And then he also said that, well, you should also put the determinant because we are interested in unnormalized measures. So you should also talk about the determinant of anyway, this path integral produces a determinant of the operator. That's of course not well defined, but there's a canonical regular zeta function regular determinant, which is well defined for smooth phi. And in particular, it's very interesting here that this is one of those determinants which the phi dependence is explicit. Okay? So, not going to go to explain you how that goes, but it's a fact that once you define this regularized determinant, its phi dependence is very simple. It's exponential, quadratic in the gradient of the phi. Similar term as what we had here. Okay. And then there's a linear term in phi. And if you remember Morris, or just my lecture on Liouville had such a term, namely linear term coupled to the curvature of the surface. And then determinant of where you put phi to 0, meaning that's just Laplacian actually. That's quite nice. What does it mean? First of all, this determinant shifts the k here. Here is e to the minus k times gradient phi squared. I get e to the plus 2, so k shifts to k minus 2. And we are usually used to having Gaussian measures where the number here is sort of, instead of k minus 2, we want it to be 1, so I rescale also the phi by square root of the k minus 2. So when that dust settles, your path integral still formal because we haven't talked about the phi. It has just Gaussian free field looking thing here. It has a curvature term like in Liouville theory. And then it has the already defined gamma part, where it just have this Gaussian field gamma with covariance which depends on phi. So this is a conditional expectation of phi given phi, gamma given phi. Integrate over gamma 0, and then the b, which is square root of k minus 2 inverse, while this change of variables is here. It's still not rigorous, right? But it's half of it is already quite nice. This thing here.
And this has nothing to do with the dual Coxeter number. So this 2 is really from the geometry. from the Witten Laplacian.
No. 2 is the dual Coxeter of SU2, yes. If you do
So
this.
how do you see it in the Witten Laplacian? Because the
No,
phi was
it
parameterized.
comes from here. It's the anomaly
Right,
formula.
I see,
It's
yes.
the 2 here.
Good, yeah,
So that's a dual Coxeter. So if you do
It is that.
any group, it's
yeah.
there. Yeah.
Good.
Okay. So gamma field has this covariance, no? So remind what it was. So the phi integral we interpret in terms of the Gaussian free field, like in Liouville, like Morris did. So there is a zero mode, and there's a Gaussian free field with covariance inverse of Laplacian. Okay. And any nice observable of phi, the bracket is defined by this determinant of the Laplacian. Never mind about that. I mean, that's there for good reasons, but let's forget about that. But in the end, you just integrate over C and take an expected value of this. Okay. Now, of course, there's a problem with the gamma, which we already succeeded defining, because there we assumed phi to be smooth, right? Because gamma is supposed to be a Gaussian, given phi, gamma is supposed to be a Gaussian field with this covariance, but phi is now not smooth. It's in the negative Sobolev space, actually. So it's obvious now what we should do, right? I mean, we should define this thing through Gaussian multiplicative chaos. Somewhere we have to do a renormalization, and that's the point where it comes. We had to renormalize this thing. We put a cutoff. We see that the only way we can get a limit is to renormalize that. And it's the Gaussian multiplicative chaos renormalization, what Morris was talking about yesterday. You just put the cutoff and multiply by power of epsilon, and you take a limit, and you get a nice random measure, when you call the Gaussian multiplicative chaos. So then you are integrating this random measure against such a function, and that's your covariance.
It should be gamma bar of V.
Yeah, that should be gamma bar, yeah. One of them is gamma bar. Okay? So here is our definition. Well, okay, I'm even formalizing it a little bit here. So let's give the following definition. Let's pick a random distribution, x and gamma. Both are in h minus s, as anything positive. We call it the Witten pair if the law of x is Gaussian free field, and if conditionally on x the law of gamma is Gaussian with covariance just like we wrote before. Okay? And now you have to do a little bit of probability to actually see that such guys exist. Let me just say that it exists as long as b is less than 1. So this is just the usual Liouville GMC condition. But the GMC exists only if 2b is less than 2, so if b is less than 1. GMC is non-trivial only then. But the law of the gamma is explicit, right? Because the law of the Witten pair is explicit. Namely, if I smear x by a test function and the gamma by two test functions h and h prime, then I can first do the conditional expectation over gamma, so I get the sorry, what is h?
It's the covariance that you define to be h.
Where did I? Good. Yeah, I defined it to be h. Okay, so it's just that, and then there is x, and I take cover expectation value over x, and I get basically by Girsanov I can shift this x away. I get sort of a covariance of x, and then I get the shift in the phi here. So the law is completely explicit. Well, not completely explicit, but that's the law. Okay, it's fixed. If the Witten pair exists, that's its law. And there we are. That's our definition of the path integral. So if I take an observable which depends on phi and gamma in our H3 space, and then the expected value is that you insert, there is this change of variables, so it's b times phi, with gamma. Gamma is gamma 0 plus capital gamma, phi is c plus capital X, and that's a Witten pair. And then I just take first conditional expectation over X, and then over gamma, and then over X, and then integrate over the 0 modes.
Sorry, when you put sub G, like starting,
Sorry?
when you put sub G, like X sub G, gamma sub G,
I want to just stress that it depends on the metric on the surface.
okay.
The definition of the Gaussian free field depends on the metric.
Yeah, so this G is the metric.
Yeah, that's horrible. Yeah. At some point I had to change it to H, but then, well, okay. There are not enough letters. Okay, there's also a genus, which is G. Genus is three G's. If you are on a higher genus surface, there are some changes. The covariance looks, the kernel here looks slightly different. There is also a co-kernel which you have to worry about. I will not go to that, but everything can be done there also. And then you could also try to do it with a gauge field, which is interesting, and that can be also done, but let's not go to that either. Let's just look at what comes out of this. So, correlation functions.
So I'm confused because previously you had already defined the path integral. So
For what?
you wrote like a correlation function. So you had yes, like
Here?
up top.
Here?
Yep.
I didn't define anything. At the moment, provided phi is smooth, I could try to define this by this formula, right?
Yeah.
But then, when I take phi also into account, I know that phi will not be smooth. So now I have to understand what to do, okay? That's why I did this sum and dance here, to define the covariance even for non-smooth phi. And then getting now wiser, I make this definition, and in the end I give this definition, okay? So this is the motivation for this definition comes from this calculation. And then the proof of the pudding is, of course, that this should now be conformally and Kac-Moody invariant, what do I get out, right? So what are the primary fields? Actually, here, these are dictated by representation theory. So now we are not in the compact group case, so one has to think a lot what there is. But let me just make long story short and say that they turn out to be in these coordinates really simple, namely just exponentials of phi and exponentials of gamma. Remember in Liouville, Maurice was telling you the primary fields were exponentials of phi. And here there are an alpha and mu there can be complex numbers. And now again these have to be defined. They have to be renormalized. So if you modify the fields, it turns out that the gamma doesn't need actually modification, but the phi needs, and and the modification is just epsilon to some power depending on the alpha parameter here. Okay, so if you do that and plug it in to the formula, the definition what we have here, then the result is that the limit exists. With a small proviso, it will be produce a delta function in the sum over the y's, the zero mode. But modulo that factor, then there is a nice limit, and that limit is invariant under diffeomorphism, and while it has a Weyl anomaly formula, where the C is the central charge is 3k divided by k minus 2. And again, in the general group, the 2 here is the dual Coxeter. And these are primary fields with those weights. Okay. And everything smells here Liouville, right? These fields and this all these formulae sort of let you think about Liouville. And actually, there is a miraculous relation. It's not miraculous once you derive it, but a priori, namely these correlation functions. So I can put arbitrary parameters alpha. Well, first of all, probabilistic theory requires some constraints on the parameters. So in the case of what I discussed here, the sphere, we need these alphas not to be too big. They have to be less than b, and the sum has to be bigger than 2b. This is very similar to what Morris was talking about, the cyber bounds. Did you talk about that? Okay. Maybe people were sleeping when you mentioned it.
Are these not complex numbers? Alpha?
Yeah, and the probabilistic, it's only for real alphas, yeah. But of course, like in Liouville, we eventually want to understand complex alphas also. Anyway, so for those alphas, and arbitrary mu's, complex mu's, you have the following formula. Namely, these correlation functions, you have endpoints here, and they transform to Liouville correlation functions at the same points, but the Liouville weights will be, the alphas will get some, will be multiplied by b. This comes just because of the stupid change of variables which I did here, so that's nothing deep about this. But then you add 1 over b. That's strange. But the more strange is that you create new insertions, namely depending on how many are here, you get more other points, okay, where you put very specific Liouville vertex operators, namely the ones where the weight is minus 1 over b. This is so-called degenerate field in Liouville theory. And also, those of you who know about conformal field theories are very nice fields because the correlation functions depend on the points y. Their dependence is governed by some differential equations. So this is super nice to happen there. Anyway, there's such a miraculous relation between the two.
Why is it n minus 2 of the y's?
Why is it? Yeah. Well, if I had, if
So
it's
there's
about
2 less somehow than those z's.
there is 2 less on general surface. It depends on the genus of the surface what comes here.
Okay.
So and on general surface, it's not only like this, but then there's also an integral over the y's. All these formulae are something which resemble formulae in integrable systems which were studied in the 70s, I suppose, where they're called separation of variables formulae, and this is some sort of generalization to it. Namely, that these formulae here are believed to emerge from this formula in the so-called semi-classical limit. So maybe I won't discuss them up to Liouville. I won't, but maybe just to finish the story, let me. I'm not sure which one is more. Maybe this contrast is nice. So we derive this funny correspondence between two completely different looking theories. One is the Wess-Zumino-Witten model with positive matrices, and one is the Liouville theory. And let's see if I'm able to tell to you. Okay, let me try. Okay, so Liouville action. The classical Liouville action. What is the? We already discussed this 2 days ago. But the Euler-Lagrange equations. So let's take. Let's put the perturbation of the field by t times some test function, and compute the derivative at 0. So you get something from here, and here. So you get from here, you get basically Laplacian of phi. And then from here you get just r, and from here you get the derivative, you get what happened? Okay. So once the dust settles, you end up with a formula like this, that, that the variation is basically the scalar curvature of e to the 2b phi times the metric, and plus something similar term e to the 2b phi coming from the Liouville term. So the Euler-Lagrange equation just tells that the scalar curvature of the metric, when you multiply your starting metric by e to the 2b phi, the scalar curvature is constant, namely is minus 2b squared mu. Okay. So this is a classic. This is how Liouville theory was used in uniformization. You look at the wide orbit of the metric, so the conformal class, and you ask whether there is a constant negative curvature metric on there. And to find that metric, you have to solve the Liouville equation. And the Liouville equation just comes as an equation that the scalar curvature of that metric is negative. That's the classical story. Okay. So extravisor or classical Liouville action finds a special metric in the conformal class, namely negative curvature. And then vertex operators, if you add them into this business, turns out that they produce then similarities in the metric. So then you're looking at surfaces with marked points and metrics with certain kind of similarities, conical similarities. A nice story there. It's a very similar story here on the H3 action. Here we talk about the gauge field. Okay? So I can take now our action and take the gauge one, which I defined to you. So let's now look at the Euler-Lagrange equation of our H3 model in the presence of gauge field. What would it look like? Okay, I have to do a calculation. Okay, and this is a bit painful. You can look at it in our paper if you are interested. So you take the derivative of that, take the Euler-Lagrange equation, and let me tell you just what is the answer. So you take such a variation, you multiply from the right by exponential of t times some matrix valued function, and the result is such that it's integral of trace a plus a dagger a star times curvature of a connection has to be 0 for every SL2C valued function. So the Euler-Lagrange equation is that curvature of a certain connection is 0. What do I mean by that? Well, first of all, curvature of a connection is defined to be its differential times its square. That's like in Young-Mills theory, okay? That's the curvature of a connection. And AH means that I'm just doing this chiral case transformation, what we already had before. I move on the orbit, the chiral orbit, which we have been discussing. And then the extra move is given by an H such that it picks from the orbit a connection whose curvature is 0. Okay? Well, do such things exist? It was proven by Donaldson that every orbit actually contains a unique flat connection, so a 0 curvature connection. So the Euler-Lagrange equation in Liouville picks up from the orbit the constant negative curvature, nice metric. The Euler-Lagrange equation of H3 model picks from the orbit now in this A business, a flat connection. So there's a super nice connection, super nice picture in both. And somehow miraculously our formula here has a connection between Liouville and H3. So somehow these two pictures here have some sort of part of the same story, because, of course, if I take the k going to infinity, b going to 0 limit on the Liouville side, I would end up to this solving classical equations. And there is even more. The vertex operator creates the conical singularities here. The vertex operators here create something which is called parabolic structures at the points. It was studied by Dr. Super nice picture. There's even nicer picture supposedly here. Namely, you could also take the so-called critical limit. This is wrong here. B should go to infinity. K should go. Oh, this is completely wrong. Don't look at the title. So it's K going to 2, B going to infinity. Why is that? You remember B was square root of K minus 2 inverse. Okay.
What was the semi-classical limit? That was b going to 0 and k going to...
That was a semi-classical limit, was b going to 0. Was that correct? I hope so. Yeah, that was correct.
Yeah.
That was correct. So I copied just wrong. All right. Okay, so the critical limit, I mean, in general case, it would again go into the dual Coxeter number. So this was argued to give something which was observed in integrable systems in the 70s and gave rise to this geometric Langlands business and all of that, this separation of variables normally and all of that. And there is some recent work where it's argued that this H3 and Liouville correspondence is actually has in the critical limit, and there's a way to sort of connect to this geometry, this so-called analytic Langlands correspondence. But let's not go anymore to that.
So here, do you mean k tend to 2 and b going to infinity?
Yeah,
yeah.
Okay. You woke up just. Yeah, so that's the story there. I think it will be the semi-classical limit is probabilistically quite approachable. So if somebody wants to study such things, that's a nice problem to look at. critical limit is certainly much more difficult because, well, on Liouville we know that b has to be less than 1, right? And we want to take it to infinity, so we need to do something more clever.
Where does that formula come from? BOC.
Which one? Which
The
one?
one we wrote on the blackboard.
This one?
Yeah.
That's what we got here when we did this story.
Define it.
Remember?
The B in that way.
Well, I was forced to define it. Remember? This guy here produced a 2. We changed the k to k minus 2. And then I just, the interesting thing is that changes k to k minus 2, then I just rescaled everything so that I could get 1 here, and then gave me that. Yeah, that was forced to us. Yep.
So in this correspondence correspondence between history and behaviour, are there any relation at the level of conformal blocks? So here you prove something at a level of correlation function.
Well, you mean, do we see that, or does anybody?
Maybe physically, any relations, anything on a level of conformal blocks.
Well, okay, I mean, yeah, I mean, if originally, yeah, there is, I mean, Teschner has been studying, I mean, Teschner's picture is that the geometric Langlands correspondence is a story about the conformal blocks, and on the H3 side, what happens is that the sort of the Zamolodchicov equations for the H3 correlation functions. So these equations transform to the BPC equations of the Liouville theory, and those sort of connect conformal blocks and Kac-Moody blocks to each other. So Teschner, that's a picture for the blocks. And then the picture for the analytic Lagrange is that the correlation functions are mapped to each other. I think on the block business, it's much less worked out as far as I understand, even on the heuristic level. Maybe Colin knows. You have been reading Teschner.
One comment about the critical point. You said it's like a flat connection. But maybe if you want to make a parallel with fluid, it may be also good to think that the path integral is over, or the action is over positive definite matrices, which is maybe as a metric on the model, and then you're touching the metric.
Exactly, yeah.
It's a kind of uniformization of the metric, such that the unitary connection is easy to complex between, make the connection fit. It's really like Liouville, where you search a canonical metric, very similar.
Exactly, yeah. So Colin is saying that H star that's a positive matrix in this two-dimensional space, and that positive matrix gives rise to, of course, a metric, and you can view that as a metric in this holomorphic bundle, and then this variational equation picks sort of a metric with respect to which the connection is unitary. The unitary connection with respect to that metric is flat. Nice geometry. And I think there's a lot to, I didn't tell you any, so basically H3 model is constructed, probably you can construct it for any group, but now it will be nice to get all this Kac-Moody business. We have a conformal symmetry we have proven, but Kac-Moody is still something which we haven't tackled. And that's something which would be interesting to do here. Once you start to do the sort of bootstrap and things like that, you should do it not for the Virasaura but for the Katsmuni. I think it's high time to finish.